Hi everybody. We're going to see if we can try one more time to get a video lecture here with atmosphere and weather. This is finishing up our look at Earth and space science and is actually the last lecture of the series in PS 105. So let's see if we can take a look. To start with, what is the atmosphere? If we take a look at this image right here, let me see if I can get a pen. Yeah, there we go. This right here, okay, and you can see this big blue arrow pointing to it too. This little bitty film of blue that you see right here, this is our Earth's atmosphere. That's it. There's not a great deal of atmosphere over the Earth. It's roughly from the surface of the Earth to outer space is roughly 60 miles, give or take. And that's not a lot. 60 miles, that's about as far as it is from, from Lawrenceville to Athens here in Georgia. So that's not a lot. But that's all of the atmosphere that is. And that all of that that's sitting above us is what's necessary to sustain life here on Earth. So what is that atmosphere? We have this relatively thin shell of gases that surround the solid Earth, and the density decreases with increasing altitude. So what does that mean? That means if we have the surface of the Earth here, as you go upward in the Earth's atmosphere, the density decreases. So the atmosphere is more dense at the surface of the Earth than it is as you get higher and higher, which makes perfect sense because of the fact that there's more atmosphere sitting over you at a higher altitude. At a lower altitude than there is at a higher altitude. Our atmosphere is mostly nitrogen, between 78 and 79% nitrogen and about 20-21% oxygen. And then there are other trace gases in our atmosphere, but primarily our atmosphere is nitrogen, oxygen. And here you have just a pie chart that is pointing that out. So that most of our atmosphere, what you should know is that most of our atmosphere is nitrogen and oxygen. We have a nitrogen-oxygen atmosphere. Now the nitrogen that's in our atmosphere that's here is actually N2, which means that it is two nitrogen atoms that are triple bonded together, which means that it doesn't react with anything. It's very inert. It doesn't react with anything, and actually we can't use it. We talked about this a little when we were doing ecology. In order for this atmospheric nitrogen to be used, it has to be fixed into ammonia, it has to be fixed into nitrates, and it has to be fixed into nitrites, all of which can be then taken up by plants and then make its way up the food chain in the nitrogen cycle. Oxygen, this also is O2, and that's because both of these two elements are found in their molecular form naturally. Now this oxygen, this is actually two oxygen atoms that are double bonded to each other, and we actually use this. Oxygen is absolutely necessary in order for you to go through cellular respiration. It is the final electron acceptor at the end of the electron transport chain, and it picks up electrons and hydrogen ions and forms water. So the oxygen that you breathe in does not become CO2. The oxygen that you breathe in ultimately becomes water. So the Earth's atmosphere is layered like a cake. So if we take a look at these layers, the troposphere, this is where most of our weather actually takes place, in the troposphere. So this goes up to about 39,000 feet or 12 kilometers. Then we have the stratosphere. That right at the edge of the troposphere to the stratosphere is where most airplanes travel, jet airplanes, like when you're traveling from one place to another across the surface of the Earth. Then beyond the stratosphere we have the mesosphere and then the thermosphere. And now notice this term right here, thermo, which means that you're probably going to have some high temperatures there. But because the atoms, the particles are so spread out, it definitely would feel colder to you. And then the exosphere. Once we get to exosphere, you're actually you're outside the Earth's atmosphere at that point in time. And this is where the space station would be. So the troposphere the troposphere itself is from the surface to where the temperature stops decreasing with height. Okay, from the surface, and what did we say that was? Looking over here, about 39,000 feet. So as you go upwards in the troposphere, the temperature decreases. And then you actually start to increase slightly in the stratosphere, and then it really increases into the thermosphere, except for the fact that, again, this would be very difficult for you to tell that it is getting larger because of the fact that the particles are so spread out at that point in time. You have very little density of atmosphere at that point. So in the stratosphere, temperature does increase with height. Stratosphere is less turbulent, which is also why most jet airliners fly at that altitude. So you'll have most jet airliners flying at that altitude because of the fact that there is less turbulence at that area. The ionosphere starts to merge with the vacuum of space. You have a lot of ions and free electrons running around in the ionosphere. The ionosphere is useful for actually bouncing radio waves off. So we tend to use the ionosphere to bounce radio waves off from one side of the Earth to the other. So this is how, like, if somebody does amateur ham radio or something like that, you can if you bounce signals off the ionosphere, you can get those signals all the way around the world. So then, what is weather? Now, a lot of people will confuse weather and climate. So let's take a look here at what the definition of weather is. When we start taking a look at weather, we're talking about localized changes in temperature and precipitation over a short period of time. All right, so if we take a look, what I've got here for you is this region on the Earth's surface between 10 degrees north and 10 degrees south of the equator. That area tends to receive much more direct solar energy than any of the rest of the Earth. That way, as a result of that, the average temperature there is higher than anywhere else, and then it will decrease. The Earth's temperatures will decrease moving from the equator towards the poles. Likewise, precipitation is at its highest around the equator, and then precipitation decreases as you go towards either pole. So as air heats up and rises and spreads towards the poles, it cools and then becomes more dense, and then it sinks back to the Earth's surface. As a result, so you get these bands of low pressure near the equator. Low pressure because the air is rising. That gives you less air pressure. And then you have bands of high pressure around 30 degrees north and south. Okay, and this creates convection currents, the same kind of convection currents that we talked about when we were looking at moving fluid. If you have an uneven heating of a fluid, it's going to rise wherever you have a heat source. Let's say this is a heat source. It's going to rise, it's going to move across to fill an empty space, cool and drop, and then come back this way. So if you have an uneven heating of air, you're going to get this constant motion, this convection current. Okay, so we get large convective cells worldwide, and that does create the stage for worldwide weather patterns. Areas of high and low atmospheric pressure, areas of high and low amounts of precipitation. So let's remember, I'm always pointing out to you misconceptions. I'm always pointing out misconceptions because it is our job as science educators to constantly talk to our students about misconceptions, because there are so many that come from the general population, and we have to make sure that our students are not falling prey to any of these misconceptions. Don't confuse weather with climate. Climate is a long-term atmospheric condition in a particular place. This is usually over about 30 or more years, whereas weather is the atmospheric conditions at a particular moment. You might have a very unusually cold winter one year, but then the average temperature in an area might be over 30 plus years might still be increasing. So we can still have global warming even if we do have a year that might have an incredibly cold winter. And that's something that people tend to have a problem with. And I often hear people say, "Oh, well, it's been really cold this winter. What happened to global warming? You scientists must not know what you're talking about." Well, it turns out we do know what we're talking about, and that's the problem with not knowing the difference between weather and climate. Wind. So what causes wind? Well, we've looked at these convection currents. If air, and I'll come up here and draw it again, if air is being unequally heated, it's going to rise in a spot where it's heated, it's going to move, it's going to sink and cool and sink, and then move back. So you will have this constant motion of air. Anytime you have uneven heating of air, you're going to get wind. So you have upward movement in an area where you have greater heating, sinking where you have an area of a cooler region, and then horizontal movement between that warm and cooler regions. So like if this is during the daytime right here, and we have sand, let's say that there's sand right here and water here, during the daytime hours, sand is going to heat up much faster than water. So that's going to cause the air to rise, and so you're going to get this kind of a constant wind blowing. That's why you always have wind blowing at the beach, because sand and water heat unevenly. They have different specific heats, and so it takes different amount of heat energy to heat each of them up. So sand heats up much faster than water does, but then water retains its heat overnight more than sand does. So this convection pattern would reverse itself in the cooler nighttime hours. So all of those types of wind result from unequal heating at the Earth's surface. And wind is actually horizontal movement of air. So wind is a horizontal movement of air that happens as a result of uneven heating. So there's your definition of wind. You might want to make sure to write that down. That could be something that comes back. That wind is the horizontal movement of air that results from unequal heating. So local wind patterns. We have a couple of important relationships that occur that will relate to local wind patterns: air temperature and air density. The density decreases with temperature. Density decreases with temperature. Hot air rises, cold air sinks. And all of this is getting right back to our convection pattern. Hot air becomes less dense, and so it rises. So hot air is less dense, cold air is more dense, so cold air falls, and so you get this constant convection motion. Hot air rises, cold air sinks. This also has an effect on air pressure. Okay, when the hot air is rising, this creates what's referred to as a low air pressure. When cold air falls, this creates an area of high pressure. Wind, like everything else, is going to move from an area of high concentration to low concentration. Wind moves from areas of high pressure to areas of low pressure. Okay, so this wind would be moving in this direction. So air generally moves from areas of high pressure to areas of low pressure. And you can see this from these images here. Warmer land, so the air is going to rise, which creates low pressure. Colder air over the water drops, creating a high pressure. So from this high pressure system to the low pressure, air is going to move from a high pressure to a low pressure. and you reverse that at night because the water is warmer at night, so the air is going to rise, so that creates a low pressure out here because the air is rising, and then you get a high pressure over the land at night, and so the wind is going to blow towards the low pressure. Wind is always going to blow from an area of high pressure to low pressure. All right, so if we took a look at global wind patterns, so take a look at thinking of those local things that we just pointed out and putting them on a more global scale, and thinking of what I brought up earlier about the area around the equator getting the most direct sunlight or the most direct solar energy and how that's going to affect things. We're going to create global wind patterns. All right, global wind patterns. So there are large-scale patterns of atmospheric circulation. There are belts of wind that circulate over the Earth. Now, you would think that that would just mean that you've got these areas that blow, where the air rises, it cools, it sinks, and then it falls. And so it's just flowing in this one area. Well, that would be true, but the Earth is also spinning. So once the Earth, because of the fact that the Earth is spinning, that has an effect on these winds. So there are belts which winds average an overall circulation in one direction, and these belts of higher atmospheric pressure that's what's going on here. So we have belts of lower atmospheric pressure around the world, and this leads to generalized atmospheric circulation. And so this gives us a model that we can follow, that we can take a look at when we're looking at overall global wind patterns. So the Earth receives more direct sunlight in the equatorial regions. Okay, in the intertropical areas, you have a convergence areas where you got hot air rising, it cools, and then it causes precipitation and falls. Cool air descends when we have higher latitudes, so moving towards the poles. And this, so you have areas of high pressure, and you have areas of low pressure along global belts here. So, and here's the diagram. So as we end up with area heating and cooling and falling back down. So that's going to create this pattern, these belts of winds that blow essentially in the same direction all the time. So here are convection currents. Now, how these convection currents are translated into surface winds, you can see how these are curved, and these curve because of the fact that the Earth is spinning. This is called the Coriolis effect. So you have the winds that are curved as a result of the spinning Earth's motion. Well, if you take a look, there are some places where you don't really have a lot of prevailing winds at all. Like right along the equator, you don't have a great deal of air flow at all, because here the air is simply rising. So you don't have a lot of prevailing winds here. If we were sailors and we were trying to sail around the world, we would want to avoid crossing this area right here. This is called the doldrums. And it's called the doldrums because of the fact that a boat stuck in the doldrums would literally be stuck because you don't really have any prevailing winds there. Horse latitudes, you get the same thing happening one more time up here where the air actually falls, and you get this area of high pressure that falls back towards the ocean. Well, what that creates is you end up with an area here where you don't really have any prevailing winds moving one direction or the other, and we call these the horse latitudes. The horse latitudes actually gets its name from the fact that ancient sailors would either have to eat their horses because they would be trapped there, or they would end up throwing their horses overboard because there was no way to support them. They were running out of food, and so they would have to eat their food. And so we call these latitudes here the horse latitudes. So we have the doldrums and the horse latitudes, but everywhere else you've got these areas of prevailing winds either blowing in an easterly fashion or a westerly fashion. Evaporation and condensation. We took a look at evaporation and condensation when we were looking at the water cycle with ecology. With water, you're always going to get this liquid to gas and then gas back to liquid. So you get this constant change. Water evaporates, water cools, water condenses, and then water precipitates back down to the earth. So you get this constant cycle, and then that water that is precipitated back down to the earth and then evaporates again, and the cycle starts all over. So this water cycle, this constant change from liquid to gas and gas back to liquid, helps create Earth's weather patterns. So, and I need for you to be thinking about how this fits together with all that we've talked about with energy. Liquid molecules clearly have a higher kinetic energy than solids. Well, when you continue to add heat energy to these liquid molecules, they will continue to have higher kinetic energy, and eventually they evaporate into a gas, because gases have more kinetic energy than liquids. Well, when those gases cool down, they will lose their kinetic energy and they will start to condense. Once they condense, that's when you get precipitation. So then, what is this saturation? When you have an equilibrium between evaporation and condensation, that would be referred to as saturation. This is influenced by temperature. Depending on what the temperature is, the air can only hold so much water vapor. Okay, the air can only hold so much water vapor at certain temperatures. Warm air holds much more water than cold air. Cold air does not hold a great deal of water vapor. That's why if you think what usually happens when we have a cold front come through and it cools off our air, well, we end up with rain. And then we end up with cooler temperatures after the rain. And all of this is because of the fact that warm air is going to hold more water than cold air. Warm air holds more water than cold air. So then what is humidity? We all know, since we're here in Georgia, we all know what humidity is. When it's so, you walk outside and you get hit with this wall of what feels like water. Well, absolute humidity is the measure of the actual amount of water vapor that's in the air at a given time. This can range from near zero to whatever the saturation limit is. And that saturation limit would be what we were just talking about, the total amount of water vapor that can be held in the air. The warmer the air, the more it actually can hold. Relative humidity, on the other hand, is a ratio. And this is relative humidity is typically what we get whenever we're getting a weather report. The relative humidity is the ratio of how much water vapor there is in the air compared to the maximum amount of water vapor that could be there. You have to think about relative humidity as kind of like your grade. The total amount of points that you earned divided by the total amount of points that you could have earned. And so for relative humidity, as the temperature is warmer, then this is going to have an effect on what the relative humidity is, because with warmer temperatures, then we've increased the amount that can be held in the atmosphere. Interestingly enough, as oppressive as it feels, air that is high in humidity is low pressure, and vice versa. Air that has low humidity has a higher pressure. High pressure air tends to lower the amount of humidity. And so we could actually do a calculation to show that if you wanted to, because if you've got more air in your, more water vapor in your mixture of nitrogen and oxygen molecules, that's actually it takes away some of the nitrogen and oxygen molecules because you've taken up their space. And water has less mass than nitrogen and oxygen, and so you end up with less air pressure. So high humidity equals low air pressure. So the capacity of air to hold water changes with its temperature. Okay, as the temperature increases, it has a higher capacity to hold water, and as the air decreases, it has a lower capacity. So higher temperature air can hold more moisture. That means the humidity is higher, but it also then means the pressure is lower. So condensation then. Condensation, this is what we think about when we hear precipitation. In order for it to precipitate, or rain, snow, sleet, whatever, then water vapor in the atmosphere has to condense. When you actually look at a cloud, you're not looking at water vapor. Water vapor is invisible. What you're actually looking at is millions of water droplets that are all together in one spot. So what affects condensation? Relative humidity. Remember, relative humidity, this is the amount of moisture that's in air divided by the total amount of moisture that could be held by the air. And then, of course, the temperature, because if we drop the temperature of that air, what's that going to do to the amount of moisture it can hold? Remember, lower temperature air means a lower amount of water that can be held in the air. So that causes a less amount that can be held. So what happens to the excess? Rain. So water molecules join together to produce a liquid, and then that liquid on the surface, you get dew, which is condensation on the surfaces. And if that condensation happens in the air, you get a bunch of droplets, and eventually those droplets are heavy enough to fall to the earth as rain. If it produces a solid, then you end up with either frost or snow. Air has to be saturated in order for condensation to occur. So, well, what are the things that can happen to cause air to be saturated? You can either, if you don't change the temperature, you add water to it. If you add water, eventually it's going to be saturated, so the water will condense. Or you cool down the temperature. If you cool down the temperature, you lower the amount of water that can be held in the atmosphere, and so that causes the water to condense. So water vapor added, so saturation, here's the saturation process. Water vapor is added to the air via evaporation, so you get more water vapor in the air. Okay, cooling reduces the capacity of the air to hold the water vapor, and when you combine the two, you end up with some sort of precipitation. Okay, some sort of precipitation. So you increase the amount of water. If you decrease the temperature, then that excess water that's in the atmosphere has to go somewhere, and usually it happens as rain. So then what are fog and clouds? Fog and clouds are really the same thing. What makes a difference is where they are located. Fog is near the ground, and clouds are higher up in the atmosphere. Fog and cloud are not water vapor. Fog and cloud are not water vapor. They're composed of tiny, small, just millions of suspended water droplets. Okay, so they are composed of millions of water droplets. And they form around condensation nuclei, which could just be simply dust particles that are in the atmosphere. So the particles about which fog or cloudlets form are these condensation nuclei. It could just be, like I said, dust in the atmosphere. we do classify clouds based on their location and their shape. We have cirrus clouds, which are really high and very curly and wispy. We have cumulus clouds, which are piled up and look like big puffs of cotton. And then we have stratus clouds, which form layers, layers over the earth. So if we look at our images over here, these would be these would be cumulus clouds, and these look like stratus clouds right here because they're forming layers. But if we look here, these are definitely some stratus clouds here. These are cirrus because they're very high and very wispy. And then these are cumulus clouds because they're big and puffy. And typically most of our storms and things like that come from cumulus clouds. So here's a diagram showing the clouds themselves. Now, and you can see, okay, so we have cirrus, cumulus, and stratus clouds. Those are the three primaries. But then we can add some things to them and get other types of clouds. Alto cumulus, alto stratus, this just changes the altitude. So a cumulus cloud that's up higher is going to be an alto cumulus. A stratus cloud that's up high is going to be alto stratus. This would be a cumulonimbus cloud. This would be a cumulus cloud that has built up and up and up and up and up. Sometimes you might call this a thunderhead because this is the type of cloud that is going to produce large thunderstorms. So the two things that come together to produce clouds: temperature and air pressure. So when you have a mass of air above the Earth's surface, if it's cooled to its dew point, meaning that it can't hold the moisture anymore, then what's going to happen is it's going to condense, and that's when you're going to get cloud formation. If this cloud formation is just pushed higher up into the atmosphere, it could get pushed beyond the dew point and you get precipitation. And there are three major causes of upward air movement. Convection, which is what we've been talking about. As air heats, it rises, and then it cools and sinks and comes back down. So we have this convection current. Notice that I've drawn this on just about everything because when it comes to weather, convection currents are so incredibly important. So convection, which is caused by differential heating, can move an air mass upward, which could create precipitation. If a cloud moves into a mountain range, it might move up the mountain, which is going to put it at a higher altitude, which is going to make it cooler and also cause it to then condense even further, and then ultimately you'll get precipitation. If it combines or collides with another air mass that has a different density, then that's going to form a cloud front. So what is atmospheric stability? So you have a stable atmosphere when a lifted parcel of air is cooler and more dense than its surrounding air. Okay, if that lifted parcel returns to its original level, and then any clouds that form, you have stratus clouds, then things tend to be pretty stable. Okay, you still might get precipitation. Okay, but you're not going to get massive storms. You're not going to get massive wind. You're not going to get, a thunderstorm or anything like that. But when we have an unstable atmosphere, this is when a lifted parcel of air is warmer and less dense than the surrounding air. So when that moves to a higher level, it will continue to rise, and this is where you get cumulus clouds, and if you have a lot of moisture in those cumulus clouds, then you're ultimately going to get cumulonimbus clouds. And that's what we refer to as an unstable atmosphere. So, precipitation. Precipitation is simply when you have moisture falling back to Earth. Okay, this is water, liquid or solid, returning to Earth's surface. Dew and frost are surface processes, and so we don't consider them precipitation because they don't fall through the air. But dew and frost are occurring on the Earth's surface when you have atmospheric water that cools beyond its dew point and you still end up with condensation. But if that condensation occurs up in the atmosphere and then the water falls back down to the Earth, that is considered precipitation. So dew and frost are surface processes, not to be considered precipitation. So when you have water droplets that coalesce to form clouds and the droplets, or when it starts to grow into ice crystals, this would be precipitation. Now if it's a solid, when it drops because it cools directly, essentially it cools directly from a gas to a solid, which is deposition, that's when you get snow. If you have a liquid that is supercooled, and then as soon as it falls to the ground as a liquid, and as soon as it hits anything, it freezes into a solid, that would be referred to as freezing rain. If it's a liquid, if the water freezes, if it condenses into a liquid and then falls, and as it's falling through the atmosphere, it falls through a layer of the atmosphere that's cold enough to freeze it solid, that's when you get freezing, that's when you get sleet. Okay, that's when you get sleet. So snow is when you have condensation directly from a gas. Sleet is when you have rain that is falling, then as it falls through areas of the atmosphere, it freezes solid and falls to the ground as a solid. It is freezing rain if it falls all the way to the ground as a liquid, but then as soon as it hits the ground and touches something, it freezes. That would be freezing rain. So this coalescence process usually happens in warm cumulus clouds in tropic ocean. This is where most of the water that ends up raining on us or snowing on us or sleeting on us usually comes from the tropics before it gets dumped on us. So clouds contain a great deal of condensation nuclei, typically salt particles. And so this is exactly what I was saying, that if you end up with forming ice crystals out of gas directly from being a gas, then that's when you have snow. If it forms a liquid, then it's either going to be freezing rain, or sleet. And then what's going to make a difference is when or if it freezes on the way down. So cumulus clouds are usually the ones that produce showers or thunderstorms. And these only last brief periods. However, it still can rain from stratus clouds. But if we get stratus clouds, because stratus clouds cover an entire area, any type of rain or storm that is coming, any type of rain that comes from stratus clouds, one that's usually not a storm, and usually it lasts for a long period of time. Cirrus clouds don't produce any type of precipitation. So cirrus clouds, no precipitation. So a little while ago I mentioned air masses as one of the ways that can ultimately cause the liquid that is in air or in gases in order to cause it to coalesce into water droplets. So what are these air masses? Well, you can take a look at this. So we have a large mass of air that has similar temperature and similar moisture content over a particular body of land. We refer to this as an air mass, and you can read this full definition of an air mass. So in here you can see our typical air masses. We have continental polar air masses, which are cold and dry. We have continental tropical air masses, which are hot and dry. We have maritime polar air masses, which are cold and moist. And then we have maritime tropical air masses, which are warm and moist. Now, think for just a moment. Which of these 4 types of air mass do you think is going to contain the most precipitation? Well, if you said the maritime tropical, you are correct. Maritime tropical air masses tend to have far and away the most amount of moisture. One, because they're warm. Warm air can hold more moisture, and they typically form maritime, so they're forming over water, and so they have absorbed a lot of evaporation. Continental air masses don't usually contain a lot of moisture, but typically if you take a look, this is the United States right here. If we take a look at this continental polar, if this is coming this way, well, look what's right here. Here are the Great Lakes. If you have this cold, dry air and it moves over one of the lakes, it's going to, because it's dry, it's going to start to absorb a lot of moisture from the Great Lakes. And if you've probably heard all around the Great Lakes, people suffering from what is referred to as lake effect snow. When you have a big dry air mass moving across the Great Lakes, then you're going to absorb a lot of moisture, and it's going to cause lake effect snow. That's why they get so much snow in Chicago. So what is a weather front? Weather fronts are boundaries between these air masses. Okay, when the air masses have different temperatures, they don't mix because of their different densities. Just like we talked about different types of crust boundaries. You know, oceanic crust is more dense than continental crust, so oceanic crust moves up underneath continental crust, and so you have that subduction zone. Well, cold air masses are more dense than warm air masses, so when cold air masses come into contact with a warm air mass, the cold air mass moves up underneath the warm air mass, and this creates a great deal of weather. So a cold front is when a cold air mass moves into and displaces a warm air mass, and it pushes the warm air mass upward. And that warm air mass is moist because it's a warm air mass, and so it cools quickly, and so what you end up with is a lot of towering cumulus clouds, and you get this a bunch of thunder clouds, or a storm front. Okay, so when this is why, like during the summer, if you have a cold air mass that hits a big warm air mass, you're going to get massive thunderstorms. So thunderstorms can be intense, but they're usually over pretty quickly. So you have a lot of water that gets dropped pretty quickly. A warm front. When you have a warm air mass that advances over a colder air mass, then the clouds, you may get clouds that form in advance, and so what you're going to end up is high cirrus clouds during the day, and so what that's going to do is it's still going to push the warm air mass is going to move upward, but you're going to get something very different because it's the warm air mass that's moving, and so that causes, you might have a large band of drizzle and fog, and it may happen over several days, but it's not going to be a storm front as if the cold, like the one that the cold front causes. Now, what about the stationary front? This is when you have forces influencing warm and cold air masses have become balanced and they stop advancing. If we were looking at a weather map, warm fronts, let's see, yes, warm fronts, I think, cold fronts, and then when you have a stationary front, you're going to get this business right here, and so they kind of stick in place. And so this is kind of the symbolism that you will see. And when this happens, you get a cold air along the north side of a front, and you get this warm air, and so it's going to stay in the opposite direction. And anyway, if you have a stationary front, you're going to end up with essentially the same kind of thing that happens when a warm front advances. Only this way, the two are getting stuck next to each other, and so what happens is you end up with a long band of rain that's going to last for quite some time. So here's what's going on here. If I have a warm air mass that flows up on top of a cold air mass, then you're going to get these high cirrus clouds and what? If we have a cold front that moves into a warm air mass and it's going to push this warm air mass up, and this is going to squeeze the water out of this, and so you end up with a storm front as a result of this. So, what about these storms? Storms are rapid, violent changes in weather. They're often associated with frontal passages. If you were to take a look at, anytime you hear about a cold front coming through, chances are you're going to get a good bit of rain. Probably going to get, especially if it's during the summertime, you're going to get thunderstorms, possibly even tornadoes and whatnot like that. So often associated with a frontal passage, you get three major types of storms, big storms: thunderstorms, tornadoes, and hurricanes. And these are not mutually exclusive. You often will find them coming in conjunction with one another. So thunderstorms, when you have intense rain and lightning and thunder. So this happens when warm, very moist, unstable air is pushed by a cold front. Okay, so you have differential heating. This thing could be pushed up a mountain barrier or along a cold front, and so what you're going to end up with is a lot of rain, thunderstorms, and whatnot like that. So if you have differential heating, it's going to occur during warm, humid afternoons where the sun has had time to establish some convection currents. And remember, warm air holds a lot more moisture than cold air. So when that large, warm air mass cools off, all that moisture has to go someplace. So even though thunderstorms can occur in any month, typically they occur during the warmer months of the year. Usually they occur during the warmer months of the year. So where we are, this would be during the months of June, July, and August. So what are lightning and thunder? Because you get so much motion of water droplets and whatnot in a thundercloud, you're going to get all of those water molecules moving up and down. Well, that's going to create a great deal of static electricity. But when that static electricity is produced, it's got to be discharged. Well, which is exactly what you see when you see lightning. So eventually that static electricity is discharged. You see it as lightning. That lightning superheats the air around it, forcing it out of the way really rapidly, and so you end up with a sonic boom, and that's what you hear as thunder. Lightning can move from cloud to cloud, it can move from cloud to ground, or it can move from ground to cloud. Hail. So what then is this hail? Well, you've seen people with golf ball sized hail falling in their yards and things like that. Hail occurs when you have ice that builds up in clouds, and it's constantly the air draft as these convection currents are happening in clouds, and it pulls the ice up, and as it falls it gets coated with more water, so it gets bigger. If it's light enough, it gets pushed back up, and so it keeps doing this and keeps getting coated with more and more water until it's too heavy, and then it falls. And when it falls to the ground as hail. So this is frozen precipitation, spherical, flattened, or irregular shapes. You have alternating layers of clear and opaque ice. So, and they do form from falling through a thunderhead, a cloud, back and forth and over again, kind of like building a candle. If I take a candle and I dip it in wax and I pull it back out, and I've got another layer of wax. I keep doing that until I end up with a big candle. Well, these balls of ice go up, they come down, they gather more, they go up, they gather more water, it freezes, and you get a bigger ball. It goes back up and it comes back down, and you get a bigger ball. And that continues to happen until the ball of ice is too heavy to get pushed back up by the thundercloud, and it simply falls as hail. Tornadoes. Tornadoes are the smallest but the most violent of severe weather disturbances. And these occur when you have intense thunderstorms, and they resemble a funnel that drops down out of a thundercloud. Excuse me, they may or may not even touch the ground. Usually when a cold air mass is forced up over a warm air mass, and you end up with violent air currents. And because of the Earth's spin, you get these violent air currents that are actually spinning in a particular direction. And that's what ends up creating a tornado. So we could have tornadoes that are 100 meters to 400 meters in diameter, and they could have wind speeds up to over 480 kilometers per hour. Most of the damage that comes from a tornado is going to be produced by stuff that is flying in these high winds. So here's an image of a tornado, and this is a massive tornado. We typically rate tornadoes and their strength on what is referred to as the EF scale, or the Enhanced Fujita scale. So an EF0 is a pretty minor tornado, 65 to 85 miles an hour. And that goes all the way up to an EF5, which is over 200 miles per hour. And this would be considered incredibly devastating. So an EF5 tornado is huge. It has massively high-speed winds, and that produces a great deal of damage. Hurricanes. So hurricanes, think of a tornado that's kind of huge. These are all storms with strong upward atmospheric motion and a cyclonic surface wind. Now remember, hot air rises, so if we consider this rising as this air twists as it goes up, you're going to create a rotation. And as that rotation gets stronger and stronger, it creates an open spot, or an eye, in the center. And so what you end up with is all of these storm fronts rotating around an area of extreme low pressure. Okay, an area of extreme low pressure. And that's what a hurricane is. So typically they're born over tropical or subtropical waters. They may or may not be associated with any particular one weather front. They're classified according to the speed of the winds. So tropical depressions are the lowest grade of, it's not really a hurricane yet, but it's a hurricane in the making. So if the winds are moving about 55 kilometers per hour or less, then you have what's called a tropical depression. And again, this is an area of low pressure, an area of extreme low pressure that is rotating. Tropical storms are a little bit more than that, 56 to 120. Once you get to 120 kilometers per hour, now you are considered, the storm would be considered a hurricane. So you have a very intense low pressure, 120 120 kilometer per hour sustained winds, and this will be with weather bands surrounding a very concentrated eye, which is the center of rotation. So here's your hurricane strength chart, Cat 1 through Cat 5. A Cat 5 hurricane is considered catastrophic. That's because you could have storm surges of up to 18 feet or more. Now, when I say storm surge for a hurricane, whenever you hear the term storm surge, that doesn't mean that the water is moving inward like this, say 4 to 5 feet. What that means is that the depth of the water, enough water has moved in so that the depth of the water has increased 4 or 5 feet. So like in a Cat 4 hurricane, think of the water level increasing 13 to 18 feet. So that's not 13 to 18 horizontal feet, that's 13 to 18 feet vertically. So the water is coming in to the point to where its depth increased by 13 to 18 feet. And here's where you have a hurricane, so that you've got intense low pressure coming up. You got everything spinning. So weather forecasting, we can relatively accurately forecast weather, although nothing is, none of that is perfect. But using weather patterns and the strong computing power that we have with our computers, we can forecast what the weather is going to be based on patterns and data. So we use a lot of instruments to collect data. Wind speed measured by anemometers, temperature by thermometers, so precipitation, so how much wind we have blowing, the temperature of the air, the moisture of the air. These are all things that go into forecasting the weather. So when you summarize all of that data to get average values and put it into a computer model, you can actually make some predictions of what the weather should be, over the next few hours or tomorrow and that sort of thing. So we can get fairly accurate forecasts up to about 3 days. After 3 days, it gets a little iffy. And so things start to get a little uncertain. And you've probably noticed that if you're trying to deal with a weather forecast and you're trying to look beyond 3 days out, then you're going to quickly start seeing that the forecast tends to change. And obviously the ocean influences this weather, and this is not something that we completely fully understand. Climate and latitude. So I've already said that climate itself is usually what we're looking at when we're looking at weather patterns that have existed in a particular place over the course of some 30-odd years. So when we think about large weather patterns over a large number of years, now we're talking about climate. Typically lower latitudes have high solar radiation. They have very small yearly variation. In other words, the temperature doesn't change. I like to make the joke that the easiest job in the world is a weatherman in the city of San Diego, California, because they have probably 5 to 10 degrees difference year round. So unlike, here in Georgia, we might have a 40-degree temperature shift in one day, and year round they're not going to have more than about a 5 to 10 temperature shift. In the middle latitudes, you get a little more variation, because you do get during part of the year you are going to get higher amounts of solar radiation than in other parts of the year. And overall you do get greater variation than at the low latitudes. And then at your higher latitudes, really high latitudes, you get the maximum amount of variation, because there's a great deal of difference in the amount of solar radiation that occurs at part of the year to another part of the year. And you can see how that works out here. So what are some things that influence regional climate? Altitude, mountains, large bodies of water. All of these things are going to, including ocean currents, are going to be influencing the climate in particular areas. How high you are in altitude is going to definitely affect climate. whether there are mountains that are there, large bodies of water, because water will absorb a great deal of heat. And then, of course, ocean currents that can bring excess energy to a place or also take energy from a place. Most of Western Europe would not be nearly as warm as it currently is if it were not for the Gulf Stream continuously moving warm or energy, heat energy, from the equatorial regions of the Atlantic to those regions that, at the latitudes where we have Western Europe. If it weren't for the Gulf Stream here carrying this warmer water up towards England, England would be pretty much cold all the time. So these things will definitely influence the climate of a particular area. And as always, I've given you a great deal of study websites here, and you definitely should take a look at. There's a lot of information in this. In this particular lecture. So go back and take a look. Make sure you do your reading for climate and weather. And with that, we will end.